Good morning, class. Welcome to our unit, Design in Timber to BS5268. So our first subtopic will be stress grading. And you find that the strength of timber is a function of several parameters, including the moisture content, density, size of specimen, and the presence of various strength reducing characteristics such as knots, slope of grain, fissures, and vein. Now, when we talk about moisture content, you find that when timber has a lot of moisture, which means it has a lot of water, we expect the strength to be very low. So the strength of timber is inversely proportional to the moisture content. Now, when you talk about density, you find that the strength of the timber relates positively with the density. When the timber has a high density, it has a high strength. Now, we look at the size of specimen. Automatically, when we have a large piece of timber, we expect it to be more strong compared to a small piece of timber. Another one is presence of various strength reducing. Now, when you talk about knots, knots can be like rods in our timber. Then slope of grain, the slope should be uniform for the timber to be of good strength. Then fissures means some unfilled holes or spaces within the timber section. They reduce the strength. Then we have vein is where now the timber, if the section will be fully rectangular, you find like some parts of it have been removed, have been chopped off. So vein will reduce the strength of timber. Now, let's go to stress, grade stress and strength class. So table 10 of BS5268 shows timber species, or what we call grade combination and associated grade stress and moduli of elasticity. Now, what we mean is that this table 10 of BS5268, you will find like we have timber classes like class C14. It gives you the bending stress, the shear stress, the compression stress, it gives you the modulus of elasticity. So you move along a row and obtain the properties of each of the timber classes. So in all, there are 16 strength classes. So the grade stress or strength class, we have 16 of them. And the most common one are we have class C14, class C16, class C18, class C22 up to class D70. Now, from there, let's look at what we call permissible stresses. So when we talk about permissible stresses, in simple terms, we mean the amount of stress this timber section can withstand without failure. Like we mean, if permissible stress of a timber is 20 Newton per millimeter squared, if you apply a load of 21 Newton per millimeter square, the timber section is likely to fail because the stress will be more than what it can accommodate. So permissible stresses are modified stresses obtained when grade stresses are multiplied by modification factors known as the K factors. Now, when we talk about grade stresses is the value you obtain from table 10 of BS5268. So the value obtained from table 10 of BS5268, when you multiply by the K factors, the result you get are called permissible stresses. So the K factors include, so we have these K factors come in different form. We have the moisture content factor. So the moisture content factor is given as a K2. So it's a K factor, but K subscript 2. Now it is in table 16 of BS5268. So you find that, as I said earlier, strength and stiffness of timber decreases with increasing moisture content. Like when the moisture content is high, in a timber section, its strength will be low. So from BS5268, you find that we have 3 service classes which can be demonstrated in table 8 and 9. So we have service class 1, service class 2, and service class 3. Now, for you to apply the factor K2, the service class of the timber should only be 3, but for service class 1 and 2, we don't use K2. So to find more about what is service class 1 and 2, you can refer to the notes on moisture content factor K2. Then another K factor is duration of loading, which is given by K3. So the duration of loading K3, we have 3 cases. We have short term, medium term, and long term loading. So you can obtain them in table 17 of BS5268. Then we have notched end factor. Now, notched end factor, it means our timber sections at their end, they are connected in form of notches, grooves and notches. So it's factor K5. Then you have depth factor, which is K7. And as I said, grade strength given in table 8 and 9 apply to timber section having a depth of 300 millimeters. So these K7 values from table 8 and 9 are only for timber sections which have a depth of 300 millimeters. So for other depth, the grade bending stresses are multiplied by the depth factor K7 defined in clause 2.10.6 of BS5268 as follows. Now, remember, the K7 value in the table is for a depth of 300. But now, if my section depth lies below or equal to 72, my K7 is equivalent to 1.17. It will be a constant. But if my depth of the section lies between 72 and 300, then K7 will be equal to 300 in millimeter divided by depth in millimeter, or that power 0.11. And then you find that we have some cases whereby maybe your section depth is more than 300 millimeter, and then in such a case, our depth factor K7 will be 0.8 into h squared plus 92,300, which is a constant, divided by h squared plus 56,800, which is also a constant. Then we have another K factor called load sharing factor K8. So this load sharing factor K8 has a value of 1.1. It's found in clause 2.9 of 5268. Now you find, like, for me to use the load sharing factor, it means you must have a system of joists. Timber joist means secondary beams which are sharing the load and transferring the same load to the main beams. Another K factor, we have compression member factor K12, table 22. So compression member factor K12 only applies to the columns and struts, because columns and struts are compression members, while beam and slabs are flexural members. So compression factor K12 can be obtained from table 22. So the compression stresses parallel to the grain given in the table are used to design struts and columns with slenderness ratio less than 5. So where the slenderness ratio is equal or greater than 5, the grade stress should be multiplied by modification factor K12. Now, from that table, you find that the table 8 and 9, where we have the grade stresses, those values are given if the slenderness ratio of a compression member are below 5. But if you calculate and find that slenderness ratio is equal or greater than 5, we have now to modify the grade stresses using the factor K12. So the factor K12 is based on the minimum modulus of elasticity. So it means when I'm calculating K12, I use E minimum, meaning E small value, not E mean to mean average. I use E, this one here, I use E minimum, irrespective of whether the load compression member acts alone or forms part of the load sharing system. So if that compression stress, this means compression stress, C means compression parallel is given by compression stress parallel is equals to compression stress multiplied by K3, which is load duration factor. So let's look at timber design. So in this particular course, we look at two. Timber design will entail design of flexural members, which include beams and slabs, then design of compression members, which we said include struts and columns. So if you want, we have page 7 showing the simple to show what is cross-sectional area, what is breadth, what is depth, what is whatever of a timber section. So let's look at flexural members. You say include beams, rafters, and joists. Remember, we know beams. These are horizontal members. We know rafters are slanting members inclined. Then joists are maybe secondary beams, beams which transfer load to other beams. We have design procedure. Now, for you to design this flexural member, step number 1, you determine the effective span of the member, which is given in clause 2.10.3 of DESIGNBS5268. So after effective span, now see the diagram here. Now, from the diagram, we have what you call the bearings, 2 bearings on either side. We have what you call clear span. Now, effective span is the distance between the centers of the bearings, or some books will say distance between centers of support. So if you say distance between center of support or center of bearing, it will be right to mean the effective span. Then now we have bending. Now, after effective span, we go to bending. Now, in bending, remember we have design moment and what you call moment of resistance. Moment of resistance, MR, is also called moment capacity. So in design moment capital M, it means moment which come from the external loads being applied to the timber section. But moment of resistance or moment capacity means the internal capability of that timber section to overcome the load being applied. So when you are designing, the design moment from load should be less or at worst equal to the moment capacity or moment of resistance of this particular timber section. So where M, design moment, is a function of applied loads, while moment of resistance is a function of the internal capability of the timber section, which is given by permissible bending moment parallel to the grain multiplied by the section modulus along the x-axis, which means zxx. So for rectangular section, remember zxx is given by bd squared over 6. Now from the diagram here, d means depth, b means breadth, then along the xx axis. So the permissible bending stress is calculated by multiplying grade bending stress. Now, grade bending stress, this is what you obtain from the table. So you multiply by any of the k factors, which is appropriate. So permissible. Now, when you see the word ADM, it means it is permissible bending. So this one stands for parallel, is equivalent to bending stress parallel to the grain obtained from the table multiplied by K2 by K3 by K7 by K8 as appropriate. It means as appropriate means maybe I'll only multiply by K3 and K8, or maybe by K3 and K7. It doesn't mean like we don't have to include all the Ks in our calculation. Depending on the question, depending on the situation, we might take K2 and maybe K3, or we take K3 and K7. We don't have to put all of them in the same equation. So now for a given design moment, the minimum required section modulus ZXX can be calculated using, now remember we said that moment of resistance is equivalent to permissible bending multiplied by section modulus. Now, which should be greater or equal to design moment, which is M. So for me to find the minimum required ZXX, basically I just divide by sigma M ADM parallel both sides. So that now after I calculate this ZZ required, I'll go to the table and obtain a section whose ZXX, section modulus along XX, is slightly greater than what I have calculated. So we go to deflection. So excess deflection in flexural members can result in damage to the surfacing material, sailing, petition, and finishes, and to the functional needs as well as aesthetic requirements. So when our maybe beam or flexural member undergoes excessive deflection, you find that the surfacing material will be damaged, even the sailing will be damaged, even petition. And aesthetic value, we mean like the shape of the house, it will appear sagging, which is not right. So clause 2.10.7 of BS5268 recommend that the total deflection, which is delta T, should not exceed permissible deflection delta P. Now, the total deflection should not be more than what is permitted, more than permissible. So in terms of equation, I mean delta T should be less or equal to delta P. So the permissible deflection is generally given by, so permissible delta P is equal to 0.003 times the effective span. But for longer span, domestic flow joist, if now your spans are more than 4.67 meters, you now restrict it to a maximum of 14 millimeters. You don't use this formula. If the span is more than 4.67, now your permissible should be 14 millimeters and not 0.003 times span. So total deflection, remember deflection comes from bending and shear force. So you see that total deflection is equivalent to bending deflection plus shear deflection. Then you go to another thing, another test we call lateral buckling. So lateral buckling, basically it means the timber section undergoes twisting. So we say occurs if a flexural member is not effectively laterally restrained, resulting to twisting sideways before its full flexural strength. Now it means lateral buckling is a mode of failure which occurs if the member is not restrained from rotation and lateral motion. So by not being fully restrained, you find like it will undergo twisting, and twisting is failure. So it's in table 19 of BS5268. It demonstrates what is a lateral buckling. So for beam with a rectangular cross section, now the most shape we use in timber section is a rectangular section. The maximum applied shear stress occurs at the neutral axis and is given by, now the maximum applied, now remember this A stands for applied, then shear stress applied is 3 times maximum shear force FV divided by 2 times area. Now remember this area is obtained from the table along that timber section. So where FV is applied maximum shear force and A is cross-sectional area. So permissible shear stress is given by, now permissible shear stress, remember we said wherever we have ADM, it means permissible. So it's given by shear stress obtained from the table multiplied by K2, K3, K5, or K8, like as appropriate means it will depend on our question, which K do we adopt, okay? So where sigma G, shear G means shear stress parallel to the grain. Then you go to bearing perpendicular to the grain. So we say applied bearing stress perpendicular to the grain should never exceed the permissible compression stress perpendicular to the grain. Now, applied is we use a permissible, we use ADM. Yeah, because we said applied come from external load, while permissible come from the internal capability of our section. So, for our section not to fail, it means applied should be less than what our section can carry. So, this is the mathematical expression of applied being less or at worst equal to the permissible. So the applied bearing stress is given by, now applied bearing stress is given by applied, which is sigma CA perpendicular. So it is bearing force F, which is maximum reaction, divided by, I'm sorry, we have B here, breadth of section, multiplied by L subscript B means bearing length. So this B here is missing. I'm sorry, students. So ensure you add this B to be F, because now remember this bearing is stress here. Stress is force over area. So if I have force here, then I must divide by area. Area should be B multiplied by LB. So permissible compression stress is obtained by multiplying the grade compression stress perpendicular to the grain. So if I want to get the permissible compression stress, which is that ADM, just multiply by this one obtained from the table, multiply by K2, multiply by K3, and multiply by K5. So then now note the following: grade compression stress perpendicular to the grain given applies to bearing of any length at the end of the member, bearing of 150 millimeter or more in length at any position. So like if you are not been given length of bearing in a question, you can make an assumption. Every time just make an assumption that the bearing is 150 millimeter, because the grade compression stresses given in the table apply to bearing of 150 millimeter in length at any position. And another point, you remember two values for grade compression stress perpendicular to the grain are given for are given for each strength class. So the lower value should be used as it takes into account the amount of when permitted, and the higher value can only be used where when is prohibited from occurring. So this is what we call when. Remember, this is a rectangular section, but because of some defect, this part is missing. So it's not completely rectangular. This is what we call when. Now, when you go to compression stress perpendicular to the grain from the table, they are giving you two values. We have a smaller value and a higher value. So unless you are being told this vein is prevented from occurring, just use the small value, because using a small value will assume you don't know if the vein is occurring or not, so that if it's occurring, you have taken a small value which takes into account the amount of vein permitted. So on our next lecture, I'll take you through an example. Goodbye, meet you in the next lecture.